please welcome to the stage Jose de Pena Paz. Thank you.
Hi, welcome. I'm Jose de Pena. Well, I work for Igalia. The reason why I'm here is that, well, we are going to talk about Linux, low memory devices. We are going to define what it is about, how Chromium adapts to that, and what we can do to make things better. So the reason why it is interesting for me is I work in several downstreams. In the past, based in WebKit, nowadays in Chromium, or one example, the LG Web Stack, and the other is nowadays is Bloomberg Web Stack also. So the problem we are going to talk about is, okay, Chromium is a web engine that is used among other places in Linux-based embedded devices. The Linux port is mostly designed for desktop-like devices. So the main thinking about the Linux port is around that. Modern desktops now usually have 4 GB at least, but way more than that quite often. But on these kind of embedded devices, we have quite often devices that have 2 GB or less of memory, and in some cases, we can get even half a gigabyte. Like it makes things a bit more complicated. Okay, so this is the spoiler. Can we run in 512 MB? Yes, but it doesn't work much great. So we are going to check this. Obviously, we can expect a 512 MB device to run as great the web platform as it works in a beefy computer. But there are some things that can be done. So in this session, the idea is first going through what uses memory in Chromium. Then we are going to check a bit what Chromium does to improve the performance when we are in low memory devices. And then a bit about the tools available for investigating, working, and making things better in that scenario. But the most important thing for me is what comes at the end, and is that if it's possible to have an open discussion, so people think about what their concerns are, how they are working with this problem, and what Chromium can do better regarding low memory scenarios. Okay, so first, let's define a bit what a low-end device is regarding memory. I mean, for Chromium, this definition is basically written in the code, and it depends on the physical memory available in the system. So it's device dependent. There has been some unification to make this definition and the API to track this the same in all platforms. But in general, we consider a low-end device in desktop to be something that is less than 2 gigabytes of RAM. And on iOS and Android, it's going to be 1 gigabyte with some caveats. Okay, in Android and Chrome OS and Linux, the scenario is that most of the low-end work has been targeted for Android. Later for Chrome OS, we have Fuchsia, we have many things around, and we have Chromecast. But Linux was not the main target of any of this work. Though the things have been evolving lately, so the API and the code is specific to low end happens to also be applied to Linux. What kind of devices are we talking about when we are seeing embedded devices that do not ship with a lot of memory? So we can have home appliances, TVs, set-top boxes, these Internet of Things small displays that we have everywhere in the house that actually use web or provide support for web. One typical scenario is that these kind of devices that have video playback support, and they may have from half a gigabyte to 1.5, usually with high resolution, but it could be full HD, but we could even have 4K devices with 1.5 gigabytes, and it's going to be really, really hard to deal with that. And if we are not targeting video playback, or if the video playback is in a very low resolution, then we could have scenarios where we have from 300 MB to 1 GB of RAM. And again, it's going to be complex, but there are cases and web platform can work also in those scenarios. We also have some kind of reference platform for what we consider low end. We can have this Raspberry Pi devices, and specifically we have now the Pi Zero family that is 512 MB. So it's very easy to try basically Chromium in that scenario and see how things work and if things are problematic or not. What I'm most interested is in the Linux problem, like making the Chromium work on a Linux device with low-end memory definition. In this case, it's usually something that is going to render using wavelength to a system compositor, or also quite often directly to a direct frame buffer. So basically, Chromium takes everything that is seen in the system display. There are different scenarios where we could have this, and they have different impacts in memory usage. So we can have like a full Chromium browser, or mostly based on the Chromium / Chrome folder of contents, and trying to run web in that scenario with these memory restrictions complicated. Sometimes it's going to be a downstream of Chromium based on Content API, maybe picking some components and some other parts of the stack as needed. We also have the scenario where we actually not shipping a browser, but a web application runtime, basically some way to show web contents integrated in the system as if they were like web application, native applications, or also the case that we basically have just one application that is all the system and it's based on web, and there's nothing else like navigating, tabs, things like that. So cases that could be really, really simple. Okay, so now next section, we are going to go through several of the owners of the memory in Chromium, the paths that usually take more memory. First one, and this one is important when we are talking about this device like 512 MB. Chromium binary nowadays is really big. The running code needs to be mapped in memory. At least the blocks that contain code that is running, right? An example of what the binary size in Chromium nowadays is, in Linux, version 128 is 235 MB. Of those, it's very easy that if the usage of that memory could go from 60% to 90% that needs to be mapped in memory. So that's maybe almost half of the memory we have in the system already taken by the binary itself. If we use, instead of taking full Chromium, we can work on top of Content API, and still the number is going to be high, but obviously it can be mitigated. Like we may be running around 120, 150 MB on the system binary and the executables that are loaded in memory. That's without even started running anything. That's memory that is there. Okay, then the traditional culprit of memory usage, one of them is basically anything that is related to painting things to the screen, to having things in the screen. So in Chromium, it's rendering and compositing stages. It's highly dependent on several factors. One is the display resolution. Obviously, targeting 4K is not the same as targeting 720p. Targeting Full HD 60 FPS video is not the same as having a small, mostly fonts, text display web page for controlling something. Having animation is not going to be the same as not having them. And the actual contents, like the video streams, but also images, the size of the images, the fonts. An example on TV. We may have a huge resolution like Full HD or maybe 4K, but the actual contents, as they are designed to be seen from a coach or from a bit of distance from the screen, then the fonts are going to be really big, and we are not going to show a lot of text. It's just things big, so the user can easily read the context of the TV. So things that are allocated, okay, the tiles for CPU rasterization, and maybe their copies to the GPU when it's needed. The actual output frame buffers. We have the font cases because we know that the GPUs are not great at painting fonts, and then we have them rasterized with the CPU. So we need to actually have them available for the GPU then for doing the composition with everything else. The images, sometimes it's copied in several flavors, like the compressed image that is cast, and then the decode image, and then maybe a copy in the GPU side as a texture of the GPU when there's no serial copy available. Yeah, the other CPU buffers that map our GPU textures. Yeah, so there can be some duplication. There are some ways to reduce that duplication with basically avoiding extra copies. Okay, and the JavaScript world and the web world in general, we have the V8 heap. V8 heap has garbage collection, and we have there what we have, like the JavaScript objects. We have the compiled code and the source code the string representation of the source code. We have arrays, strings, data, also objects pointing to native memory. So yeah, the garbage collection fortunately can be tuned, but it's not easy to adapt to very, very low-end memory scenarios where we may have like peaks of usage taken out of memory, and then, okay, garbage collection happened, but the problem is that in this peak, we may end up going out of memory. And yeah, as I said, resources for rendering the actual web contents and the browser UI. So yeah, CSS, JS code, and the images, the fonts, the actual HTML. We map those when used from local files, we map directly. And if it's remote files, basically we have the disk cache and we keep them in memory somehow when we are using them. Okay, there's another problem is that modern web frameworks, we quite often have this thing about minifying files and having huge frameworks as a big JavaScript, and then we work on top of that. They are minified, but still, we need to use more memory to keep that around. We do not filter what is actually used of those frameworks. We need more time to parse, because quite often devices with low memory, they usually do not have also a lot of CPU power. So we also need to be careful regarding that. So we found that quite often we lose a lot of resources in this kind of frameworks that they can kind of get from CDN, the full framework, JS, and that's loaded at the start. And loading time, the starting time of the web page is slow, but still, after that, we are still maintaining a lot of code, a lot of representation of the code in memory. Okay, so let's go through what Chromium provides for low memory devices, right? First, we have this API. This is going to be around all the code base, basically just checking, okay, if we are in a low-end memory device, we are going to do this and this and this. And the idea is having lighter paths regarding memory for some scenarios. And then we have this a bit newer API that is all-enabling part of the low-end memory optimizations, because we say, okay, we are in a not so much constrained device, but still it's going to be better to save a bit of memory because performance is going to be better because of that. Okay, so the first problem is that, the main problem here is that these low-end memory optimizations are not always available for all the ports. On some cases, it's basically in the Java code of Android. So the equivalent implementation in Chrome, in the Aura implementations, it's not going to have these optimizations. And in other cases, it's just basically worded. So the feature the performance optimization is only available when you are running on Android or maybe on Chrome OS. This has improved along the time, so most of the optimizations are available also in Linux, but not all of them. There's more work to do. Another problem is basically that it's kind of ad hoc thing. So people that investigate in memory problem space end up using the CPI for other things, but it's not like something formally documented too much. I know it's Chrome. We don't expect anything to be formally documented, but even for the start, it's just a bit guessing that on the hot patch, you finally find that there's this calls to each low-end memory device, and you say, okay, this is an optimization for the low-end memory case. There's also not much tracking, and I couldn't find good tags in the good tracker for memory-specific problems. So there's a mix of things that are somehow related, but yeah, maybe it would be nice to have some kind of tag for unifying the investigation and for unifying the people working in this problem space. Here's a list of things that are controlled by low-end memory. I'm not going to go through all of them, but yeah, basically you see that we tune the behavior of Chromium so it takes less memory. It has impact on the performance on several cases because we have less caches, we have slower paths, or we even skip some optimizations, and we even skip some security features or reduce or minimize some security features because we cannot maybe afford having some extra processes, things like that. Then using the code base, you are going to find other memory tunings, other parts of the code that are dependent directly on checking the amount of physical memory. So it is going to say, okay, if we are, how much memory do we have in the system? 512. Okay, we are in the range from 300 to 1 gigabyte. Then we are going to apply these settings. This is independent of its low-end memory device. So in the end, it adds a bit of less tunability because it's very specific to a specific case of the code. So it's maybe designed for a very specific scenario the developer tried, and that may not work so great in other parts. What's a solution for that that is helpful is basically moving to use numerical parameter as much as possible. So basically, we can tune per case and per device, even from command line, the behavior, or in which cases we are going to add different levels of memory, depending on that. Okay, and what do we have for working on the memory problem space? We have, I think that the nicest thing or the most work thing here is memory infra. So basically, we have in the increment tracing, we have a way to collect every few seconds, or how you tune that. We can ask the components that support this, okay, how much memory are you taking and why? And it also allows to define some responsibility or ownership of that memory, because we have memory that is accounted in the render process, but also in the browser process or even in the GPU process. And you want to actually make those memories be accounted only once. So you can realize, okay, the impact is not so much, even if it's 10 MB, if it's not the same as, okay, we are counting it 3 times because we are counting it in several processes. So yeah, it's going to simplify that. But the problem with that is that we need actual support in the components for providing the information. This is an iterative process. As the more components identify that have memory problems, we just can add an implementation. If you own a component that takes memory in a significant way and is not supported in memory infra, then you should do that. It's something that is important. Then for the web world, we have in the Chrome DevTools, we have the memory tab, we have heap snapshots, and we have allocation tracking, and several ways to represent information. It's especially useful when you try to understand the memory usage pattern in the JavaScript part of the world, and how it impacts, well, the DOM allocations, things like that. And then we have like most traditional tools that are not specific to Chromium, and that can see things that are not already accounted in the tools that we talked about before. We have algorithms, screens, we have all the sanitizers provided by LLVM, and we have like SMAPs. Using SMAP, we can just take a look to what is taking memory and actually the blocks that are taking memory to identify the applications and to identify if the memory usage is as high as we think or not, and where memory is going. So wrapping up, this is kind of a list of contact points, but they are not working very well because there's not much activity around them. So we have the memory channel in Chromium Slack. There's not much activity there. There's the Google Group Memory Dev. I think it hasn't seen a message in 2 years, so it's mostly abandoned. Yeah, if you want to see documentation about this, docs memory, there's a README. There's another file that is, I added the link there, but it's actually achievements, something like that, that shows a lot of examples of specific optimizations that have been done. So it's really nice if you want to see examples of how things can be done to improve memory usage. Okay, so this was the main part of the presentation. And now we are going to the open discussion. So basically the idea is if you want to share your sad story working in the memory problem space, please tell us. Please, it's the time to talk about. Anything valuable, any downstream implementation that okay, we have this and it would be nice to have that upstream. Great. And then we have this, what Chrome could do better for the memory problem space. What we could do as a community better so things are easy to work on. And there's a secret, I mean, quoted, secret slide at the end with my wish list of what could be better in this problem space. But yeah, it's first, let's get the voice to you.
When you describe or characterize a low memory device.
Sorry.
Thank you. When you characterize a low memory device, are you talking about something that has a unified memory architecture, so the GPU and main processor memory are sharing, or do you find that these usually have separate? And then how important is the GPU memory utilization on either kind of device? And like how important is it to you to be able to measure and quantify that in these?
Yeah, so yeah, basically most, I say that the big majority of low-end memory devices, they are going to have unified memory, some kind of unified memory architecture. That's, from memory point of view, that's nice, because it allows to share memory buffers that are mapped both for the GPU and the CPU. But still, that needs some work, and that's GPU specific, sometimes architecture specific. So you actually need to make sure that you have all the pieces in place so you can implement a zero copy. That's a path that's available in several parts of Chromium that allows to reduce the memory usage. About the GPU memory investigation, that's actually a complex problem because many times we don't have visibility of what is happening internally in GPU. So basically, we allocate textures. Okay, we allocate some buffer, the frame buffers, whatever. But then we unnoticeably allocate buffers because the GPU is actually doing a copy because the format of a texture is not the one it wants to render, or because a texture is locked for rendering a frame, and then you need to do a shadow copy to actually have everything working. So yeah, the tooling for getting the memory usage is not great. Is GPU specific in quite often. That's something that it will be really nice, not only about Chromium problem space, but almost if you're working on Wayland Compositor, if you're working on something that is graphic intensive in a low memory device, it's really hard to know what is happening with memory without counting what you actually allocate. That you know that this buffer is something that you allocated, but quite often you are missing other parts that are internally allocated by the GPU driver.
One sec. I had a question from the chat. Will low-end stuff be indicated in the user agent?
I don't think it's indicated in any way.
Okay.
Someone in chat had said that there are user agent hints. Oh, sorry.
Okay.
So someone in the chat had said that there are user agent hints about that, but I didn't have the details. I just saw the chat pop up on the screen.
Yeah, the thing is that that's another way to adapt. Basically, that the web contents can decide, okay, we are on a low memory device, we can try to avoid several of the features of the UI.
Hi, we work in YouTube living room on a very far downstream fork of Chromium, effectively, and it's called Cobalt. And so we are on a route right now to kind of be less custom and like more aligned with Chromium. All of the low memory things that you mentioned are kind of very familiar to us as well. Our typical devices are as low as like half a gigabyte of RAM, right? I think on the content side, on the GPU memory and so on, there's a lot of tricks that you can do. Like you mentioned several of them, like reducing the consumption and reducing on what's kept resident. What really scares me is the resident set size, because our current RSS is about like 25 megabytes or so. And going to a full Chromium, that's going to be a huge jump. Like, are there any tricks or any ideas or any thoughts or threads going on around that, on how to reduce that side or how to manage that better? Besides just reducing the binary size or kind of turning features off.
Yeah, I think one of the things is that Chromium has been designed. Well, the policy is that the configurability happens in the runtime and not in build time. So that's problematic because in the end, if you take the default Chromium, is going to support many options that for embedded cases or for a specific embedded case is not useful. So that's one thing that we have. But if you compile a kind of trimmed Chromium based on Content API, just taking components, that's a way to reduce the binary size part. Quite often, the other optimization part is actually checking the contents you are playing. Quite often you see, okay, we have this huge CSS, we are not using almost anything. I say, please reduce the web content. And maybe that's one of the things that we could try as a community to try to give, not sure if core web vitals is a way to do that, but hinting somehow that the memory usage is a lot. And that things could be better with reducing memory usage, maybe exposing that better in DevTools, so web developers can be aware at least that when they're introducing something, it has a cost in memory, and that's going to make things worse for low-end devices. That's something that likely we want to do.
And last question, and then we'll move on to the next one, I believe.
Sure.
Yes, I'm also on the Cobalt team, as the earlier question. I have a little bit more technical question, like what you earlier addressed, that the GPU driver sometimes allocates extra textures to do copies and things like that. Have you noticed any difference in using GLES or Vulkan and how you can control that or address that? Another question, you can pick and choose which you answer, is do you have any insights on what your experience is with memory allocations used by video decoders?
Yeah. My experience right now, in my case, I'm working more in a scenario where I need to make sure that all web frontends work. So basically, sometimes it's going to be WebGL, sometimes it's going to be Vulkan, sometimes it's going to be regular web contents. So I need to take care of all of them. My feeling right now is that using Vulkan, the memory usage can be reduced, but it needs to be done right, as everything. As a good DOM CSS application is going to be better if you avoid extra composition, or extra layering creation, or just some very complex filter that is going to add penalty somewhere else, or in CPU calculation sometimes, or add fonts that are really big, and then the glitches are going to take a lot of memory. These kind of things, obviously, they are there. So basically, you basically need to give the tools to the actual developers to make sure that their content is as efficient as possible. If then they do mistakes about, you can hint, okay, please don't do that, and that's it. But we need to support even not really great web pages. Unless you're in a scenario where you have embedded devices that the UI is fully controlled by you, That's another case. In IoT, that is quite typical. Then it's fine. It's on your own. You make sure that you communicate with the web content developers. Okay, it's better that you don't do this animation. This kind of things. An example that is quite typical that has an impact. Okay, we are going to have this animation that animates on the font size. That's really nice from the design point of view, but it's terrible. Basically, performance, because you are going to need to rasterize many times, and that's going to actually take memory, but also performance. So, it's junky. The animation is not great. Please don't do that. Don't animate on font size. Things can be done better, yeah, but it's going to be hard.
All right. Thank you very much, Jose.
Yeah. Oh, one thing.
Oh,
Are we done with the time? No. We are done, right?
yeah. Let's. You have something real quick? Go for it.
Yeah, it's just my wish list is people interested in the problem, join the Memory Slack channel. Downstreams, please contribute in discussions, but also with patches. Maybe a performance bot for low-end memory case, basically that we can check if there are regressions even with low memory. And yeah, more tuning, more being able to adapt to low-end memory cases, using more numerical parameter and using more low-end device modes ones. And that's it for the wish list. Thank you. And yeah, I hope you enjoy the rest of BlinkOn.
All right. Thank you, Jose.